So today I did some mathematical work, namely I counted the number of lectures remaining. And the result was 8. I will try, we'll just have a conversation with Henry regarding this, but I will try somehow to do what I wanted to do in these 8 lectures, but still now it is impossible just to push something to the next time and so on, because time is pressing. So now what we are doing now is classification of complex simple Lie algebras. And it actually consists of 3 parts. First, which I'm going to do today, maybe it shouldn't be first, but I will begin with this. This is a purely geometric consideration of root systems. Precisely, not root systems, something related to it, but you can say root systems. Precisely, we did it for root systems on the plane, in the dimensional case. Second, we will have to root systems regarded in this part as purely geometric object, not related to any Lie algebras. Still, Lie algebras do have roots. And then we will have to prove, well, something more stronger than I'm going to say now, but first of all, that if 2 Lie algebras have the same or isomorphic root systems, then they are isomorphic. Actually, more is true. But this is definitely true. And the last part, if you have a root system, is there a Lie algebra with these roots? The answer is yes. But this depends on very explicit constructions of Lie algebra. Some of them we know, like SL. Or SO. Some of them will appear, including this exceptional Lie algebra, which I will not construct here. I can give you a reference, but you can find it easily. So this is the third part. So what I'm going to do today is some very elementary geometry. And it is the first time in this course that I'm going to say something which is not written in my notes, because now we sort of go in line. I will again try to fill this gap this weekend, although this weekend I have too many dramatic things to do. But I will try to do it, mostly today. So, what are we going to consider? A vector space, actually a real vector space. A real vector space with Euclidean structure. It is the real part of H or H star or whatever. The inner product is the Killing form. Okay? Okay. Then, in this space, there are some vectors. Roots, if you speak of H star, H alpha, if we speak of H, it's not important because everything is canonically isomorphic. And these roots satisfy some properties which we know, some geometric properties. For example, if alpha and beta are 2 roots, then some expression is an integer, 2 in the product alpha and beta divided by alpha is an integer, but not only this. We know something about series of roots and so on. Now, at some moment, for a short time, we forget all this about roots, and so just we have a system of vectors in Euclidean space, which satisfies some very strong geometric conditions. And we want to know how to observe all possibilities for these systems. This is what I'm going to do today. The first thing that actually I will consider not precisely this. I will rather consider, well, some other things which I'm going to define now. So, this is what. we have roots. Now what we do? This is a system like this. Remember, we have systems. This is a simplest example. Now I just cut this picture into two pieces by a plane, quantum measurement plane, through the origin. Actually in an arbitrary way, although it may be more convenient to make this way not quite arbitrary. And in this very arbitrary way, I call this roots positive and this roots negative. You can switch it. So what's important, visible from the picture, that if alpha is first, every root is either positive or negative. And second, if non-zero root, certainly. If alpha is a positive root, then negative alpha is a negative root, and vice versa. In reality, it is usually done in a very slightly different way, in a more specific way. I think that it is enough for us. So positive and negative roots. Now just new notion, simple positive roots. Nothing can be easier. A positive root alpha is not simple if alpha is the sum of two positive roots. That's all. So simple roots are not sums of positive roots. Here, these two roots are positive. Next thing, not only in this picture, but always. First, simple positive roots form a basis in the whole space H star. Also, the inner product of two simple positive roots is always non-positive. On this picture it's negative. The angle is obtuse, but it may be 90 degrees. But so why? The first thing, if so, the angle between simple positive roots is at least 90 degrees. Why so? You see, if there are simple positive roots alpha and beta with the angle less than 90 degrees, then you know it is true that actually both beta minus alpha and alpha minus beta both are roots. You know, because say the root series starting at beta with the step alpha should be symmetric with respect to the line perpendicular to this. We show that at least one should be here. Of these two roots, alpha minus beta and beta minus alpha, one should be positive. So if alpha minus beta is positive, then alpha minus beta plus beta is alpha, and alpha is not simple. Nothing can be easier than that. Okay? Okay. So all the angles are, all the inner products are not accurate, meaning that all the angles are 90 degrees, 120, 135, 150. Now, I want to add to this. So far it's not purely geometric, but it will be purely geometric in 2 minutes. I want to say that not only simple positive roots form a basis, but actually any root at all is a linear combination of simple positive roots with coefficients which are either all positive or all negative. No mixture. So you cannot take 5 times one simple positive minus 3 times another positive. It will not be a root. So every root is a linear combination of simple positive roots with coefficients all positive. If it is positive, then all positive. If it is negative, then all negative. So why so? Suppose that alpha 1, alpha n, a simple alpha r, rank. Simple positive roots. Now, what is very clear, right from this picture, that it is not possible that a linear combination of these simple positive roots with positive coefficients, when I say positive coefficients, at least one is positive and all are negative, is 0. You see, they all are on one side of this hyperplane, so we take the linear combination with coefficients which are at least one is positive and all non-negative. It shouldn't be 0. It has a non-zero component in this direction, right? Now, very simple thing. Imagine that still this alpha is linearly dependent. Coefficients, some positive, some negative, right? Let us write this relation of linear dependence in this way. Actually, greater than 0 both. So some roots with positive coefficients, some roots with negative coefficients, and the sums are equal. This means that the whole linear coefficient is 0, okay? Denote this by gamma, and let us try to find the inner product, gamma and gamma. It will be the sum right? This is very much non-positive. This is very much positive. So altogether it is less than or equal to 0. But this is actually non-negative. And moreover, if it is 0, so this implies that gamma is actually 0, and gamma is 0, which shows that everything is impossible. Okay? So this is a basis. Now it is clear, just again from this picture, that all positive roots are linear combinations of simple positive roots. They should be linear combinations of simple positive roots because simple positive roots form a basis. But with positive coefficients, it is clear from this picture. Everything is on that side. And the same for negative. So actually all roots are linear combinations of simple positive roots with coefficients of the same sign. This means that the number of simple positive roots is equal to the rank of, to the dimension of H, rank of our Lie algebra, which is also denoted as R. Very interesting. Now we draw following Dinkin, we draw the following graph. We draw R points. They correspond to simple positive roots, not all roots. Then, if two roots, if the angle is 120 degrees, we connect them by an edge. If the angle is this, we connect them by double edge. And if the angle is this, we connect them by triple edge. If the angle is 90 degrees, we do not connect them at all. In these two cases, in this case, the length of these two roots are the same. In these two cases, actually, they have different lengths. And we can also draw this thing to indicate which is longer. It is not always done, but it means it's possible. So this means that the length of this is length of this times 3, or 2 here. There arises a graph which is called the Dinkin diagram. The fact which I will certainly comment not today, that actually this graph, so full information of the geometry of simple positive roots, implies the full information of all the roots at all. All what we know about roots, about series of roots, is sufficient to say this. And also is sufficient to give an isomorphic class of the whole Lie algebra, which is less clear, but we will do this. I hope that next time, but who knows. So what we are going to do now is to classify all possible Dinkin diagrams. And if you don't know, I draw them R points. This is called AR. I don't remember which is B, which is C. Maybe this is BR and the same is CR. This is DR. This is G2. This is F4. Because of symmetry, I do not need to indicate which is bigger. This is 6. E7 and this E8. Purely geometric theory, which I'm going to prove. Maybe now. Maybe I will have to postpone something to the next time, but so far I still hope to do it now. This is all the possibilities. By the way, in dimension 2, which we know, the possibilities are, so R is dimension, is dimension space, rank. G2, yes, A2. And also B2 and C2 are the same, if R, unlike the case when R is greater than 2. B2 and C2 are the same. So the possibilities are this A2, B2 same as C2, and G2. Dimension 3, it will be A3, yes. It will be B3 and C3, which are different in this case. But it is all. And this fact is proven by pure elementary methods. And I'm going to do it now. Since I haven't written that, it is possible that I will confuse something, then I will make corrections next time. You have questions, Bob? No.
Sorry, my
Hands,
hands.
yes. No questions about this? Yes. So, yes.
Can the DR go off to the left?
Directions?
You had more dots to the left.
1, 2?
No, I don't mean a fan,
no.
but I mean a
Yes, R is arbitrary. Everything can be extended to the left as far as you wish. Not this, not exceptional. In the case now. By the way, this inches 2, 4 is always means the number of dots. You can count if you don't believe. Yes.
So then the D3.
D3 is D3 will be the same as A3.
Yeah.
This is an isomorphism actually between SO6 and SL4. Algebraically. Well, I didn't say one thing. These diagrams which I draw are connected components. A diagram may be disconnected, may consist of several pieces, but this means that there are two groups of simple poised roots which are orthogonal to each other. That means that the whole system of roots actually is reducible. So there are two systems in two orthogonal spaces, and we just consider them together. We consider irreducible systems, which correspond to connected graphs. Yes. There is a term which I will definitely use in my notes, admissible system. So since I do not consider anymore real algebras, at least at the moment, I use just system of vectors. And they're called admissible if they satisfy properties known to us regarding inner products and so on. I mean system of simple positive roots, not of all roots. In particular, all the inner products are non-positive and so on. Angles are such and such, so everything, lengths are such and such. And we are going to classify these systems. First, let me consider, so alpha 1, alpha r are my vectors. Let me do the following thing. The sum why not? It's not zero, because alpha r's are linearly independent. So this, I say r, not r. I, and I from 1 to r. So this is what? We should take products of this with itself, right? It should be 1. So r times and plus the sum alpha I, but alpha I alpha j divided by alpha I alpha j. And now please look at this. What do you think about r? It is square, so 2, right? Yes. This, what do you think about, yes. So the expression is known from you, from your lessons of linear algebra, is cosine of the angle, without 2. The angle is obtuse, or right. Cosine of such angle is non-positive, if you don't know. When you multiply by 2, then the value will be -1, well 0, yes, 0. -1, negative, well no, but negative square root of 2, and negative square root of 3, right? So I can say that this certainly, every sum is less than, if it is not 0. It was surprised how much follows from this, because this should be positive. This is r. And then we subtract from r a certain amount of numbers. Numbers correspond to what? They correspond to all pairs with non-orthogonal. They correspond to all connections in the Dynkin diagram. right? And since it is positive, we can see that the number of summons here is, let me say, at most r minus 1. Because if I subtract r ones from r, it will be not very much positive. It is a very strong result. Just imagine that we have a graph, connected graph, with r vertices, and at most r minus 1 edges. What do you think about this graph? I personally think that first the number of edges is r minus 1, and second that it is a tree. Right? Very interesting. Fact number 1. Questions, please. So the Dynkin diagram is a tree. Okay? 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 Okay, good. Now let us decide the following thing. We have some vertex in some point in our graph. And we just look at different connections of this point with other points. This is alpha, and these are betas. I want to say the following. First, that alpha is not orthogonal to any of betas. Second, all betas are orthogonal to each other, because no connection, no cycles in this tree. So betas are all orthogonal to each other, and alpha is not orthogonal to any beta. And everything is linearly independent. These alphas and beta are all what? Are all simple positive roots. I want to say that we have some amount of mutually independent, mutually orthogonal vectors, plus one more vector which is not the linear combination. Then certainly I can find a gamma in a space spanned by all this, which is actually orthogonal to all betas. Right? Very interesting. So this alpha, together with all betas, form in some space of dimension, well, I didn't know the number of betas. I can write beta k, dimension k plus 1. So this is k1 plus 1 dimensional space, and betas and gamma form there a system of mutually orthogonal lines, right? Now, what do you think of the following? Cosine squared of the angle of alpha and gamma I do not know, no, alpha and beta. I do not know what to think about this. But actually, if you have a system of orthogonal lines in some space, and one more line, and the sum of squares of cosines of these angles is 1. Some people call it Pythagorean theorem. You understand? So the sum is 1. This sum is, but what about these numbers? These numbers first, all are non-zero, absolutely. But I want to say that this gamma maybe gamma is not necessarily in our system, but still cosine squared. It should be positive because, and these numbers are each of them. These numbers at most, not perpendicular, these vectors. At most one quarter. Can you imagine that a sum of numbers, each of them is this 1/4, and some positive number is 1? I think it is possible only in one case, when you have three, at most 3 numbers here. Moreover, if you have 3 of them, well, make some computations with square. Yes, with 3 of them, they should also be 1/4. So this picture is not realistic. In this graph, actually, in this graph, we have alpha at most 3 connections. And moreover, the same inequality will say more to you. If these 3 connections are all single, then yes, it's possible. If one of them is double, then we have only one more. If one of them is triple, then we can have anything else. For double connection, this is 2/4. For triple connection, this is 3/4, right? Yes. By the way, already from this, we have the following thing. If we have in our graph at least one triple connection, then we have nothing else. Right? Triple connection prefers to stay alone. Which corresponds, by the way, to my classification, which is not on the board anymore, but you remember. But we have more, actually. We have some things which are prohibited. For example, this is prohibited. Right? And this is prohibited. Then a very simple trick, very geometric. So again, I want to use the words admissible system. And admissible system is not necessarily full. In 5-dimensional space, we can have an admissible system of 3 vectors. Why not? Now, suppose that we have in our graph a subgraph like this. Something here and something here. Then, this corresponds to some connections here, double. And this corresponds to an admissible system. Then we can collapse this, and it will be also an admissible system. Why so? The following trick. If we replace all these vectors by sum, just imagine. Then, if this has connection with something, in the products will, this is a computation which I even don't want to write on the board. All the inner products will stay. Say if the length of all these things are 1, then this will also, the length of the sum will also be 1. Computation which the angles are 120 degrees. So the inner products say the inner squares as 1, inner products are negative what? 1/2. Then we compute the square of the sum and you will get 1 again. So such a thing. Which means that as soon as we have these things which are prohibited, this is also prohibited. And actually anything else, yes, this also, and this is prohibited. Right? Having this, we actually have almost full classification. With, however, one small thing which should be settled. The fact is that, by the way, this is prohibited not only as a full system, it's prohibited as a part of a system. Because actually, if you take a connect part of your graph, it will be also. So what remains? Certainly this, yes. We can forget about it, but still. Then this. It remains, it's okay. Then this. And then this. This amount of dots here are arbitrary. Here also, and here also. No questions so far, because I have almost nothing to say. So we have, this is all possibilities for our system. The first two are okay. We will do nothing with them, they are possible. The remaining two, I can say, so here we have two numbers, P and Q. The number of dots on the left and on the right. And I want to prove that either P is 0 or Q is 0, well, this equation is symmetric, or they're both equal to 1. No other possibilities. Any other possibility will can be brought to a contradiction by simple geometric argumentation. Here we have three, P, Q, and R. And actually, I can formulate only one condition on P, Q, and R. This should be greater than 1. This should, if P and Q, yes, this should be greater than 1. So here I formulated everything. I have 7 minutes, and it's more than enough to prove this, because it's very simple. But you understand the statements. So actually, this system is an admissible system only in these cases, and this system is an admissible system only under this condition.
Wouldn't be enough to get classification, though, right? That latter one for 1 over P plus 1 over Q plus 1 over R wouldn't be enough.
Yes, so it contains the D case, 1, 1, and any R.
Right, but if one of them is only one line, then you could have any length in the other two.
One line is separate. I suppose that P, Q, and R, well, I don't remember, P, Q, and R. I believe that P, Q, and R should be including this point. Well, we will see from the proof. Not written. No. This certainly exists also. But I consider the case when actually there exist three tails. The proofs are more or less the same. The first thing. So we have P here, we have Q here. This I denote as alpha P here, alpha P minus 1, and so on, alpha 1. This is beta Q minus 1, beta 1. The lengths are different. I can suppose that the inner product of alphas, the inner square of alpha is 1, the inner product of beta is 2, for example this, because of the double connection. Now let me consider the following thing, gamma. Let us take its square. And it should be positive, right? No, actually we need, let me do it differently. It is alpha, it is beta, and gamma is alpha plus beta. Or actually gamma is, actually I don't need anything else. Alpha and beta, no, I don't need the full sum. What is alpha alpha? With your kind permission, it is, so the square of alpha is 1. The sum of the squares, right? And also, there are connections between alphas. There are p minus 1 inner products. P minus 1 inner products with which are equal to negative 1/2, right? Good? The sum of the squares, I don't remember the formula, is right I squared. So not written, excuse me. Actually, I have it written in my, but I will not. So let me just say what the computation is, and then you do it yourself, or I will write it, both, I will write it mine. So you compute this, and you compute this, which is very simple, because actually only these two are connected. So we have everything, right? And then you apply to these three numbers your favorite Cauchy-Schwarz inequality. And from this your favorite Cauchy-Schwarz inequality, you see precisely a relation for P and Q, which means that P and Q are either one of them is 0 or PQ is less than 2. This will appear from the Cauchy-Schwarz inequality. Before less than 2, which means that either P or Q is 0 or both are 1. P and Q are non-negative numbers, right? So probably it should be rather like this. Yes, probably if Q should be the number of dots not including this. Yes, so this is the computation, which gives the first result. The second result, I have only 1 minute, so I will not write it, but I'm obliged to write it in my notes, and actually you will not need this. Again, you have this system. And you take the similar sums of these dots, of these dots, of these dots, with coefficients like here, starting from the end, 1, 2, 3, and so on. Same here, same here. And what you do, you actually compute the inner products. They are orthogonal to each other because these two are not related. So what you have only inner squares. This inner square should be positive. And this gives 3 inequality, and as soon as you sum them up, you will get this. There's 1 over P divided plus 1 over Q plus 1 over R should be greater than 1. And this gives you your classification. Frankly, I don't think I need to return to it next time, because everything is done. I will write this simple geometric argumentation in my notes. And this is all for today.